Thank you very much for the nice introduction, and thank you for the organizers for organizing this follow-up conference after the initial trial during the corona pandemic. And thank you, of course, everybody here for being here in person. My name is Kai. I'm from right now from the University of Augsburg. But, well, you're forgiven for not knowing that, for forgetting that, because I've just started, like beginning of this month. The work that I'm going to show you was all done at the Max Planck Institute for Intelligent Systems in Stuttgart in Germany. And, well, now I've just changed to a new institute because the director is retiring at the MPI for Intelligent Systems. So, yeah. Anyway, so let me just jump right in. The work that I'm going to present here was done in collaboration with several people at MPI. Most foremostly Max Birch in the group, essentially my group here in Stuttgart at the Intelligent Systems MPI, and then we've got a second MPI to make it more complicated, the MPI for solid state research, and there it's a PhD student, Lukas Powalla. I also thank my theory collaborators, Karin Efrischer-Sitter at the University of Duisburg-Essen, and Daniel Maillot and Gita Balakrishnan at the Warwick University for fabricating the material, essentially growing the crystals of the system that I'm going to show you. And finally, also the synchrotrons where I performed my work. Anyway, so let me start with a brief outline. I'm going to start talking about general introduction, what am I doing, what I've done about systems, and I'm going to explain very briefly the imaging technique that we're using. Then I'm going to show you some properties of different compositions of iron germanium telluride. This is the van der Waals magnet we're looking at. What this composition does is in respect to the stability of skyrmions and what stabilizes skyrmions in general. Then I'm going to talk about actual formation of skyrmions. That is a bit of a follow-up on the writing question that we had in the last talk. And finally, a little bit of an outlook on another van der Waals system that is very promising for high-temperature applications. So, for the introduction part, let me talk about magnetic skyrmion. You've heard that already a couple of times, so I'll keep it brief. They're chiral spin structures, as Berger pointed out, and they have this special topology which derives from a sphere by just, well, putting spins on the sphere. You can imagine that as you project the sphere down into a plane by opening it up on one pole. For example, here you open it up in the North Pole so that the background becomes the North Pole orientation, up in this case, and your South Pole becomes the down orientation and is the core of the skyrmion. And now the orientation on the sphere here defines the domain wall, which means you can also generate a second type of skyrmion by combing spins around the sphere, and you end up with an a different in-plane orientation of the domain wall, and this is called a nail skyrmion on the left and a block skyrmion on the right, depending on the orientation of the wall. So, why skyrmions? Well, just talked about that quite a bit, so I'll also keep that brief. One of the earliest prospects was to use it in racetrack memory devices, and these racetrack memory devices could store information just like a hard drive, but as in a solid-state shift register, so you wouldn't have any moving parts. Instead, your information comes to the read and write head instead of the other way around. So, one option is, as Berger pointed out, we have a skyrmion sitting somewhere, and that's 1, and the absence of a skyrmion is a 0. But that might be not the best option because these gaps could relax together and you change your information. One alternative is for the standard skyrmions to use a 2-lane system where you have an energy barrier in the center, and you end up with 2 lanes, one corresponding to 1, the other one corresponding to 0. And if you operate that in a lattice phase, so that the skyrmions are essentially on their minimal size and they can't overtake one another here, that would also make for a safe data storage option. However, there's more options. The racetrack is just one proposal, and it's not actually really using the 2D properties of skyrmions, which is one of the most interesting parts of their behavior. So one other option would be to use them in so-called reservoir computing applications. Reservoir computing means that you essentially start with, well, your input information. You have, let's say, an array that corresponds here to an image. Then you feed this array through different leads, through different contacts into a reservoir. This does something to the reservoir, and you read it out with other contacts on the other side. So our proposal for that was done by Karin's group while she was still in Mainz, Karin Efrischer-Sitter's group. Was to use essentially a reservoir of skyrmions and domain walls in dilute array, where you end up with, let's say, a contact here, a contact there, and then you pass current through it. And then something happens that looks a bit like shifting rocks in the side of a riverbed. So let's say you have very strong input, which corresponds to very strong neural activity. Then you start shifting around the magnetic textures, and you create path of low resistance. By creating path of low resistance, you then afterwards can read that out, and you can detect that this path, well, has low resistance. There must be an active connection. And this kind of proposal has both memory properties as well as synaptic properties in one go. For example, when you shift them just a little bit, then they will relax back to the original position. So this is kind of a short-term memory effect. While if you shift them quite a lot, it's kind of a long-term memory effect because you permanently alter the magnetic textures inside of the reservoir. So this is kind of an effect where you could use the 2D properties in a more detailed way. But for this, you need to understand properly what the skimming texture does under specific conditions, and you need to know how to create certain states in the system. So to do that, to get more of an experimental idea of what's happening in the system, we do scanning transmission X-ray microscopy, STICSM for short. That's a synchrotron-based technique. We're mostly performing that at the synchrotron BESSY in BESSY 2 in Berlin. And the general idea is that we have, well, a synchrotron that magically generates X-rays. We don't need to care about that for the moment. We monochromase them to one absorption edge so that we can only sensitive to one element at a time. That makes it easier to distinguish elements. We can go deep into a sample, et cetera, et cetera. And then we focus these X-rays with a zone plate, that's essentially an X-ray lens, onto a sample. The X-rays come out of the sample on the other side, and we just count them with a photon detector. The cool thing is now we pick up all the information on the magnetization within the spot size on the sample. And this is usually in our case between 15, 20-ish nanometers. And by pump probe means, we can also do time-resolved imaging of this reproducible processes with a time resolution of 40 to 10 picoseconds, more or less. And this is what the magnetization of a wire device, for example, looks like when it comes fresh out of the machine. What you see here in black are essentially contact pads, gold stripes that contact the sample. On the background here, you see essentially nothing. That's a membrane. There's no magnetic material here. It's transparent for X-rays. And this bar here is a magnetic wire with spin textures inside. So what you see here as a dark bright contrast inside of the wire is pure magnetic contrast, just as it comes out of the machine. So whenever I'm going to talk about skyrmions or orientation of bright and dark contrasts, then let's say white means up, dark means down, and that's essentially the message you need to take away from this. Anyway, so let's talk about what we do in FGT. What's a van der Waals magnet and why is it interesting? So van der Waals magnets, it's important to know that they have a van der Waals gap, which means they are comprised of sheets of magnetic material in this case, which are stacked together with a van der Waals gap. So there are no covalent bonds between these layers, but they're just laying on top of one another, combined by van der Waals forces, held together by van der Waals forces. So that makes them really easy to exfoliate. Essentially, you can take them off of the crystal, you end up with a sheet, up to down monolayer levels, and you can stack them together in devices. So we're ending up with a Lego-like structure where you can combine these different layers to create new devices. And these generate really clean interfaces because you have a monocrystalline material that you exfoliate and just stack together. And the exfoliation process tends to be comparatively easy by ripping off material from a crystal and taking these flakes and creating devices out of them. And at least for experimental tests, this is all totally fine and works out nicely. So this is what a flake usually looks like in our experiment. Optical image, where we see here, this is the magnetic material laying on the membrane. And if you look at it magnetically in the chamber, then you see here, for example, stripe states or skyrmion states, depending on the conditions. Sorry, the brightness is not really good for the image right now. So we exfoliate them, we generate flakes, we generate devices out of them, and then we look at the magnetic texture inside. So now let's talk about what this texture, what the state diagrams look like and why we need to know the history dependence of them. So let's talk about first what happens when we just sweep the field. This is just a simple field sweep. We go from negative field to positive field and look what the sample, check what the sample looks like. So in the lower part here, we've got uniform magnetization in negative direction, and then we go into uniform magnetization positive direction. So it just flips in a hard axis, and an easy axis flips over and is done. Now if you warm it up, you see a typical behavior of crystalline materials, where it goes through a stripe phase into a uniform phase, and near TC we've got skyrmion pockets. This is kind of similar to what you expect in a B20 compound, for example. There's, however, also different histories that we can apply. For example, we can do a zero field cooling, where we go through TC from high temperatures, go down, and then sweep the field up and down from the center position. Of course, you end up with a symmetric phase diagram this time, but this time you end up with a much, much larger stripe domain phase. So you can extend the phase where you can get stripe domains already quite easily by just cooling through TC by zero field. You can also do this cooling, but in field. And now you don't extend the stripe domain phase, but this time you extend the skyrmion phase. So in this case, we cool at 20 millitesla and sweep the field up and down. And here we get a very extensive skyrmion pocket. Yes?
How do you determine the phase boundaries?
This is all imaging. We look at the picture. Otherwise, it would be very difficult. You're right. But this is just done in the STICSym. We look at the system, we check what it looks like, and then we get either a point in uniform, stripe, skyrmion, whatever. This is because we started in an asymmetric state here. So we have 20 meters here applied, and then we go down, and yeah. Okay. So in this case, you end up with a skyrmion state, and that means that depending on the history, you can achieve up to 5 different magnetic states, completely different configurations under identical conditions. So for example, we can freely select between a stripe or a mixed state or a skyrmion state. So far to essentially the history dependence. Now let's talk about the dependence on composition, what the composition of the van der Waals system does to the system. For this, we have here essentially van der Waals Fe3 minus X. So 0 is Fe3 germanium telluride. And here we have also X equal to 0.37. So we have a lower iron composition. And that already changes the magnetic property quite significantly. Here we see, for example, a significant change in skyrmion density. And also it changes, for example, the magnetic moment and the Curie temperature, but not so much. What it actually does, it quite significantly changes the anisotropy in the system. And we're not quite sure what exact mechanism is behind that, but it seems to be the coupling between the van der Waals layers that causes this behavior. And it actually changes the anisotropy up to a factor 4. So this is actually quite significant change compared to only a few % that we see in saturation magnetization or TC. So this is actually an option to tailor your magnetic system into a desired state. For example, more stripe-like, more skyrmion-like, and so on. So with this, we have a handle on what kind of state we want to be in, depending on what history the sample was in before, or was put through before. The stability of these skyrmions is another question. And here, our results indicate that they're mostly dipolar stabilized, but they're still chiral. What do I mean by that? Well, we can do a field cycle, field cooling into a skyrmion array. This is essentially this state again. And then we change the field and expand the skyrmions in one direction. And we end up with these loose honeycomb-like lattices. And these honeycomb-like lattices is something that you see commonly in systems that are dipolarly stabilized. So this is an indication that the skyrmions here have a significant dipolar stabilization component, where the dipolar interaction keeps them in the skyrmionic phase. However, we also see that the domain walls in the system are Néel, and they're all Néel type, homochiral. So there's also still a DMI present in the system, which is currently still a big debate in the field where it comes from. It's currently not very clear what the actual origin of the DMI in the system is. This is still under investigation. Anyway, so Now that we know we have skirmins, we can stabilize them, and we know where they come from, let's talk about the generation in a nanocontact system. For this, we need to first fabricate a device. A device, in this case, we can generate by patterning, for example, here, contacts on top of in our case, membrane to look through them. Then we put a flake on top. This is this greenish area. Cap the flake with an insulating material. In our case, it's hexagonal mononitride. And this layer here is a graphene sheet, which we use to contact us on top. So we have essentially, if you look from the side, we have a silicon nitride substrate, we've got the FGT, we've got an insulating layer, and we have the graphite that just couples it into the next third contact. And now we can shoot a nanocontact through it vertically. Essentially generate a hole in the HPN layer, and the graphene forms a nanocontact with the FGT and allows you to pass current through it locally inside of a 2D sheet. So essentially, at one point you get a current, everything else is untouched by this. So even in a 2D area, you can selectively now write at one point. So what does it actually look like? Oh yeah, I forgot. The contact is actually also very small. It's far less than 100 nanometer. We assume it's around 20 nanometers in the resolution limit of our technique. This is what it looks experimentally. So you see here the contacts. This is the big FGT flake. And here in this area, we've got a little nano contact that then looks essentially like this. So this is after passing a DC current through it, where you see a couple of stripes growing out. This is just the growth of stripes mediated by thermal effects and by current. And when you apply DC current, we always see these little stripes growing out. Okay, but not so interesting. But if we apply an AC current pulses in a nanosecond regime, we don't generate stripes anymore, we just generate skyrmions, and exclusively skyrmions. And the number of skyrmions is then depending on the voltage of the pulse and the duration of the pulse, and can be tuned from one skyrmion, from a single skyrmion that's generated, up to a sparse array around the contact, which always follows a certain outline. So there seems to be always a circular area, a ring, where the skyrmions are formed, and everything else, like inside the ring or outside the ring, is not written. So you can nicely, rather well predict where they will pop up. I don't have time to explain the exact mechanism, but if you have any questions about that, just ask me afterwards. So now that we have generated them, we could theoretically now generate a device, and that's essentially what we're working at the moment. Let me instead show you a quick outlook, since these results are not quite ready for presentation yet, on iron 5 germanium telluride. This is a different van der Waals system. Essentially, it's similar because, well, it's still the same components, but it has a higher iron content. And this is very particularly interesting because this van der Waals system has a very high Curie temperature. Usually van der Waals systems have comparably low temperatures, and for any kind of device, of course, you want it to be as high as possible. This particular material is promising and has been studied in different forms for coming in annealed and in quenched states, meaning that once you grow it, you can either cool it down very quickly, this is the quenched one, or you heat it up for an extended period of time, allow the atoms to rearrange and to relax into different positions, and that's the annealed one. Usually the quenched one shows really interesting properties for, for example, squid and crystallography measurements, and we just wanted to look at the state in Stixon to make sure that it's actually a good crystal, let's put it that way. You'll see in a moment why. This material is also comparably stable versus oxidation, which is in general, of course, a problem once you deal with like monolayer thicknesses of the system, because if you have iron in the system and you've got a monolayer of it, it does not really like to come in contact with any kind of air. So here we've got the saturation magnetization versus temperature of one of the quenched flakes. What you see is in blue, the cooling cycle coming down from the quenched as grown part. And you see that it, well, increases, and something funny happens around 100 Kelvin, a bit above 100 Kelvin. Then you cool below 100 Kelvin, it comes back, and it follows a different loop. And this different loop, once you reach the room temperatures, and you go back, will be the permanently stable phase afterwards. So something has happened in the divide, in the flake. There's a morphological change that's happening in the flake, and that changes the way the magnetization reacts inside. So we wanted to have a look at that in STICSM and see what's actually happening in the flake. And if you look in the flake, I hope it's visible, the contrast isn't really great, you see like veins of different iron content. So the quenching of the material freezes in different iron areas, which means that this material is very homogeneous and not really suitable for, like, for example, racetrack or reservoir or whatever applications. Which means there have been a couple of studies on this material, and it must be very carefully checked if the material that these studies looked at, is actually presenting these veins or is homogeneous. And interestingly, the annealed one is perfectly homogeneous and shows skyrmionic states even at high temperatures. And also, depending on the exact parameters or the growth thickness, etc., it shows also in-plane contrast, which could be used for spin wave applications in van der Waals systems, which is actually really interesting because spin waves, especially in the vertical direction, in the thickness, should change once you approach the monolayer limit. So this is, in particular, a very interesting system for high temperature applications, therefore. All right, so let me conclude. We've got magnetic phase diagrams investigated in different compositions of iron germanium telluride. The iron content seems to be massively changing anisotropy in the material, and therefore can be used to tailor the magnetic states. We've got an idea of how to prepare 2D capable skyrmion writing devices for by nanocontact current injection in van der Waals flakes. And I showed you that the quenched F5GT systems are massively disordered or can be massively disordered at least, and needs to be checked very thoroughly, while the annealed ones seem to be perfectly suited for spin wave on skyrmion applications. All right, thank you very much for your attention.